Okay, welcome back to Integral Calculus. So far, I've tried to convince you that integrals are a useful thing to be able to compute. So, talking about fundamental theorem of calculus, how to compute them, what they can represent in terms of rates of change. In this video, I'd like to go over some properties of integrals that can help you apply them to various situations and also do things like make using the fundamental theorem of calculus easier. Okay, so this is a bunch of different properties of integrals, and let's go ahead and get started. First of all, integrals are additive. So let's say we have, so this is property one. Suppose we have a function. I'm going to draw lots of these today. We have an f of x, and we are looking at an interval a to c. Yes, c, not b. So we have the area is going to be the integral from a to c, f of x dx. Okay, so that's saying that this area here is, well, the integral, right? But what if I have some third point in between a and c? So if I have any b inside here, what I can do is I can break this region up into two pieces. I can say, well, I've got this stuff over here, and then I've also got this stuff over here. So what I'm doing is I'm taking the integral from a to c, which is the full area, and I'm breaking it into smaller pieces. I have the integral from a to b, f of x dx, plus the integral from, from b to c of f of x dx. That can be useful in all sorts of situations where maybe the function looks one way on the interval from a to b and the function looks different on b to c. Maybe it's increasing here and then decreasing on another place, or it's piecewise defined and things like that, and you really want to break it up and deal with each piece separately. It says you can do that, and it's clear why it's true, right? Area just works that way. Area is additive. So yeah, great. Okay, so what's next? Integrals are linear. So I don't really expect you to know what linear means, but I will show you. Linear basically means that they play nice. When something is linear, it plays nicely with addition and multiplication by constants. Okay, so when I say an integral is linear, what I really mean is that you can pull out constants and you can break up sums, just like you can with limits, just like you can with derivatives. So if c is a constant, and f and g are functions, then what I'm saying is that if you want to integrate on any interval c times a function f of x, so you've just got that extra constant in there, you can just pull it out and have c times the integral of f of x by itself. It should look very familiar from, well, derivatives, right? You can pull constants out of derivatives. You can also pull them out of integrals. And if you want to integrate a sum of functions, say f of x plus g of x, then that's easy too. Oh, not plus, equals. You can just break that up. Both integrals go from a to b here. So I'm not breaking up the region, I'm breaking up the integrand. Oh, by the way, the thing inside the integral, the function, is called the integrand. So that's f of x dx integral plus the integral a to b. Ooh, I do not know what happened there. A to b g of x dx. Okay. And, well, one reason you should believe this is true is because the fundamental theorem of calculus says you can integrate by finding antiderivatives. And since derivatives work this way, you can pull out constants and break up sums, then antiderivatives should work that way too. Another way is you can think about area. So I'll just show you with the constant one. Let's say we have some function f of x over ab. And we know we get this area from Riemann sum, so we have some little rectangle here. Let's say this is the width of dx, and then the height of this rectangle would be f of x. You could say f of xj, but for some x in here, the height is f of x. If you multiply f of x by 2, the dx stays the same width, and you're just stretching by 2 in the y direction. So 2f of x would look like this. And then you'd be looking at this sort of rectangle when you found the area, and this height would be 2f of x. So the area of the bigger rectangle is going to be 2f of x dx instead of just the height of the smaller one, which would be f of x dx. but one dimension stays the same. The x dimensions aren't changing, and the y dimensions get stretched by that too, so the area gets doubled. Okay? Okay. So yeah, let's see one quick example of this. Just in practice, it always looks weird when you write things out abstractly, but in practice it's pretty easy. So say I want to look at the integral from 0 to 1 of x squared plus 3 cosine x. And, well, what can I do? I can break it up. I can pull out constants. So I could say, well, I've got this x squared plus here, so I can just break off the x squared, and then plus the integral of 3 cosine x, but I can also pull out the 3, so I've got something like that. Not too bad, right? And you've been doing this with derivatives for as long as you've been studying derivatives, so it really shouldn't be that surprising that it works for integrals too. Okay, so what's next? Well, this is kind of an application, I would say, but you can find areas between curves. This is property number 3. It's kind of an application, but I'll call it property. Area between two curves. So say we have some f of x, and it is greater than or equal to g of x, at least on the interval that I care about, which is always is ab. Okay? So we have one function is greater than the other one. Here's my f of x. Here's g of x down here. And I'm only looking over an interval from a to b. Then, well, what can I say about that? What if I want to find the area between f of x and g of x? So I don't want all the area down to the x-axis, I just want this area here. Well, it's actually not so bad if I think that the integral from a to b, f of x, that is all the area under f. And I should mention, I'm drawing this all with positive functions, but if one or some of the functions are negative, it all works out just fine. It's just easier to visualize with positive functions. So I'm saying area below the graph, but I always really mean between the graph and the x-axis. So here, because f is positive, the integral of f of x is all the area under f, and that includes the area under g. So that would be, let me see if I can find a better color here. So that would be all of this stuff. That's the integral of f of x. Okay? Now if I integrate g of x, that's just the area under g. So that's just going to be this part. Okay? And the area I want is the black area. That's what's left, right? That's this stuff in here. That's the area I wanted. I said I wanted the area between f and g. Well, I just take all the area under f and I subtract out the area under g. So the area between f and g is, well, it's the integral of f of x minus g of x. Oh, sorry. It's the area under f minus all the area under g. I'm just taking the blue stuff, that's the area under f, and I'm subtracting the red stuff, and I'm left with the black. Okay, but because integrals are linear, you can put that minus sign inside. You can combine the two integrals into one, and you can actually just make it simpler. You can say this is the integral from a to b of f of x minus g of x dx. Okay, so that is how we get the area between two functions. We just integrate the difference of the two. Okay? Okay. So moving on, what else can I say? Well, so far we've done a lot of stretching and stuff on the y-axis, and you know, f and g are both kind of, their values are on the y-axis. We can also do things with the x-axis. So I showed you we can break it up. Integrals are additive because area is additive. You can also go backwards. So suppose we have a function from a to b. We have an f of x here. Told you I'm going to draw a lot of these today. How would you interpret the integral from b to a of f of x dx? So the lower number is big, and the top number, the top limit of integration, is small. So, what are we going to do about that? Well, how I think of this is that the bottom number here is always the starting point, and the top number is the ending point. So basically what we're doing is we're starting over here, and we're going to the left as we accumulate area. Okay? If you want to get into the formalities of this, you'd look at the Riemann sums, the sum from 1 to n of f of xj delta x, and your delta x's would be backwards. But we'll just think of it in terms of dx's. So normally you think dx is a small change in x, and you start on the left and go to the right. But if I'm integrating from b to a, I'm going to start on the right, and I'm actually going to be going to the left. So the thing to realize is that's the same as going the other way. All you do is introduce a minus sign. Okay, so the y values, the f of x's are exactly the same. The dx's absolute value is exactly the same. The size is the same. The only difference is it has a minus sign instead of a plus. So if I want to go the other way, if I want to go from a to b, f of x dx, all I have to do is introduce a minus sign and say, well, now I'm going the other way. Okay? So if you want to flip the a and the b, or we call those the limits of integration. If you want to switch the limits of integration, you can. You just have to introduce a minus sign. Okay? And it seems like maybe you'd never want to do that, but it actually comes up all the time, as we'll see as we do more of these sorts of problems. Okay, so one last property here. What if you want to estimate how big or how small an integral could possibly be without actually computing the integral? Well, those are called bounds. You want to bound the integral, or sometimes we'll just call them estimates for the integral. And well, how can you do that? The first thing to realize is that this should be obvious from area considerations, but if f of x is less than or equal to g of x on AB, then which function do you think is going to have less area underneath it? The smaller one, right? And that is exactly how it works. So the integral of f of x, remember that's the area under the small function, is less than or equal to the area under the big function, dx. No problem, right? Seems obvious if you think about it in terms of area, which you should. Okay, so that has some important consequences, but before I can talk about this, let me just mention one thing that we're going to need. What happens if you integrate a constant from a to b? So say I have some number m, it's not a function of x, it's just f of x equals m. If I integrate that, the antiderivative is mx, right? Or an antiderivative is mx. So, well, I can just evaluate that from a to b with the fundamental theorem of calculus, and I get mb minus, let's say bm minus am, which is b minus a times n. You can also see it in the picture. If my function is just m, and I want the area between a and b, it's the area of a rectangle, where this length is the side of the rectangle, that's b minus a. The height is m, so the area is b minus a times n. Okay, so what can I say about integral estimates? Well, one really nice consequence of this is that if you can find numbers that bound your function, that tells you numbers that will bound your integral. Okay, so the theorem is this. If there are numbers, or we'll call them constants, there are constants, little m and big M, such that, remember S period, T period always means such that m is less than or equal to f of x is less than or equal to big M for all x in the interval from a to b, then all you need to do is integrate those things. So I'm kind of treating f of x as the function, and then in my thing up here, g of x is just capital M, or g of x equals little m. So you can integrate all three sides of this inequality, and they stay the same. Little m is smaller than f, so the integral of little m is smaller than the integral of f. So the integral from a to b of m dx is less than or equal to the integral from a to b f of x dx, which is less than or equal to the integral from a to b of big M dx. But nobody really wants to integrate those, right? We already know what they are. You wouldn't leave that as an integral. So the area here just like I showed you before, that's this piece, m times b minus a, is less than or equal to the integral of f over ab, which is less than or equal to the big M integral is just going to be big M times b minus a. Okay? So in the picture, what I'm saying is that I have some f of x here on maybe an interval from a to b. And I have some little m that's always less than f of x, so a horizontal line. F never goes below that horizontal line. F never goes above this horizontal line. And I'm saying that this area, which is m times b minus a, that area is smaller than the integral of f, which is the area just under the curve, and that area is smaller than this rectangle. So the area under f kind of fits in between these two rectangles, this one and this big rectangle here. Okay? And that is very useful if you don't want to integrate your function because it's really hard to find an antiderivative, but you still want to know something about the area underneath. Okay? So those are some basic integral properties. We will certainly use these all the time in class as we go through and learn more about how to use integrals. And with that, I will see you in class.